Hello everyone, I am Faizan Khan from Sri Venkateshwara College of Engineering. I am studying in first year second sem data science branch in Ferrari section. Thank you for being here today. I am going to speak to you about applications of integral calculus. In the next few minutes, I'll be sharing insights and information that I believe will be both informative and thought provoking. So without further ado, let's dive into the presentation. Okay. In this time, we have got integration calculus in mathematics subject. We are going to know first contents of what we are going to do in the presentation. First one, introduction, and further we'll go with the application. Introduction. Now, first we'll know what is integration. Integration is the inverse of differentiation. In other words, if you are doing the reverse of the process of differentiation, you are just doing integration. The following example shows y equals x square dy by dx equal to x. So integration of dy by dx equals integration of 2x dx equals x square. Means when we are doing the differentiation of x square, we get answer as 2x. When we do the integration of 2x, we get the answer as x square. Means it is inverse of differentiation. Integration of the function with respect to x we are doing here. Means dx means we are doing with respect to x only. Dy means we are doing with respect to y. We developed the concept of definite integral to calculate the area below a curve on a given interval. In this section, we expand the idea to calculate the area of more complex regions. We start by finding the area between two curves that are functions of x. Beginning with a simple case in which one function value is always greater than the other. We then look at cases when the graphs of the functions cross. Last, we consider how to calculate the area between two curves that functions of y. Means we are going to calculate the area of the curves lying on some axis. Now we can tell like x-axis also. Now first we'll know what are the applications. First one, areas between curves, determining volumes by slicing method, volumes of revolution, cylindrical shells, arc length of a curve and surface area. Physical applications means applications of physics like moments and center of mass, growth and decay, hyperbolic functions, etc. are very important and which include the methods of integration. Okay, first one, areas between curves. Just as definite integrals can be used to find area under curve, they can also be used to find the area between two curves. Means first we are using definite integrals to find area between one curve and an axis. Now we are going to find the area between two curves which lies on particular axis. To find the area between two curves defined by functions, integrate the difference of the functions. If the graphs of the functions cross or if the region is complex, use the absolute value of the difference of the function. In this case, it may be necessary to evaluate two or more integrals and add the results to find the area of the region. Sometimes it can be easier to integrate with respect to y to find the area. The principles are the same of which variable is used to has the variable of integration. Means it depends. If we use with respect to y, it will be will be taking the area of y. So they are telling that if we consider the with respect to if we do the integration with respect to y, it will become very easy. Understand in deep this slicing method. If a solid does not have a constant cross-sectional area, we may not have formula for its volume. In this case, we can use a definite integral instead of formula. If we don't have formulas, we can use integration. Okay, a definite integral to calculate the volume of the solid. We do this by slicing the solid into pieces. Means if we slice here the cylindrical means which we have taken the shape in the figure, if we slice it, it becomes circles. It means many pieces of circles, and then adding those estimated volumes together. The slices should all be parallel to one another, and when we put all the slices together, we get the whole solid. Means we are going to calculate the volume of each or particular circle, and then we are going to put it together and we'll get the volume of the complete shape. Next one, volumes of revolution cylindrical shells. First, we are going to know what is solids of revolution. If a region in a plane is revolved around a line, that plane, the resulting solid is called a solid of revolution, as shown in the following figure. Means which one you are seeing that it is a solid of revolution. The method of cylindrical shell is another method for using a definite integral to calculate the volume of solid of revolution. Means here we are taking cylindrical one. Okay, there are many shapes, but we are taking cylindrical. And this method is sometimes preferable, either the method of disk or the method of washers, because we integrate with respect to the other variable. In some cases, one integral is substantially more complicated than the other. The geometry of the functions and the difficulty of the integration are the main factors in deciding which integration method to use. Means the method which we are going to use will be depending upon the difficulty level. Means which one is easy we will prefer, however, that only. Okay, we are not going to prefer the difficult one. Okay, further, the next application is arc length of a curve and surface area. We can find this by using integration. Let's know how. The arc length of a curve can be calculated using a definite integral. The arc length is first approximated using line segment, which generates a Riemann sum. Taking a limit then gives us the definite integral formula. The same process can be applied to the functions of y. And the concept used to calculate the arc length can be generalized to find the surface area of the surface of revolution. Means which one we learnt, that solid of revolution. Now we are going to learn the surface of revolution. The integrals generated by both the length and surface area formulas are often difficult to evaluate. It may be necessary to use a computer or calculator to approximate the values of the integrals. Means sometimes we have, as everyone know, integration is complex. We use particular calculators to calculate it. Okay, to help us find the length of each line segment, we took at the change in vertical distance as well as change in horizontal distance over each interval. See in the figure, as I have presented in my presentation, because we have used a regular partition, the change in horizontal distance over each interval is given by del x. The change in vertical distance varies from interval to interval through though we use del v of vi equals f of xi minus f of xi minus 1 to represent the change in vertical distance over an interval of xi minus 1 comma xi, as shown in the figure. Means if you see this figure, you can know that we have represented the change in vertical distance in the method that f of xi minus f of xi minus 1. Okay, next one. Further, the physical applications. Several physical applications of the definite integrals are common in engineering and physics. Definite integrals can be used to determine the mass of an object if its density function is known. If the density is known, the mass of the object is calculating the mass of the object is very easy. Work can also be calculated from integrating a force function or when contracting the force of gravity, as in a pumping problem. Definite integrals can also be used to calculate the force exerted on an object submerged in a liquid. Means the objects which are present inside the liquid, they are getting experience with the force. We can calculate the force which is being experienced by them by using this integration, definite integrals. We examine some physical applications of integration. Let's begin with a look at calculating mass from a density function. We then turn our attention to work and close the section with a study of hydrostatic force, mass and density. Okay, we can use integration to develop a formula for calculating mass based on a density function. First, we consider a thin rod or wire. Means see here in this figure, we are taking a rod or wire as an example. Oriented the rod so it aligns with the x-axis. Means it is aligning with the x-axis. with the left end of the rod at x. Means the rod at x equals a, you can tell, and the right end of the rod at x equal b. See, has mentioned the figure. Note that although we depict the rod with some thickness in the figures for mathematical purposes, we assume the rod is thin enough to be treated as one of the dimensional object. Okay. So then next application, calculus of hyperbolic functions. Hyperbolic functions, calculus of hyperbolic functions. Hyperbolic functions are defined in terms of exponential functions. Term by term differentiation yields differentiation formulas by hyperbolic functions. These differentiation formulas give rise in turn to integration formulas. With appropriate range restrictions, the hyperbolic functions all have inverses. Implicit differentiation yields differentiation formulas for the inverse hyperbolic functions, which in turn gives rise to integration formulas. Means inverse of integration differentiations inverse is integration, as we have discussed before. The most common physical application of hyperbolic function are calculations involving catenaries. Okay, then we'll know with an example what are these catenaries and how integration is being used. Okay, one physical application of hyperbolic functions involves hanging cables. If a cable of uniform density is suspended between two supports without any load other than its own weight, the cable forms a curve called a catenary. Means the curve which is being formed by the cable or a wire, or in the example you can include the chain also. Catenary, which is called as catenary. Catenary, high voltage power lines, chains hanging between two posts, and strands of a spider web all form catenaries. The following figure shows chains hanging from a row or posts. Okay, thank you. Please like, share, and subscribe my channel. So be connected. Thank you.